All right, so today we're diving into Reichenbach's common cause principle, RCCP. And, since you're a philosopher, we're really going to dig deep into what it means for how we think about causes, like how things happen in the world around us.
That sounds fascinating. RCCP is a really big deal in the philosophy of science, lots of debate around it.
For sure. So let's just start with the basics. How would you, break down RCCP? Especially, in a way that another philosopher would get.
Okay, so picture this. You see two things always happening together, more than just random chance. You'd think, oh, one causes the other, right? But what if neither one actually makes the other one happen? Reichenbach said there's got to be a third thing, a common cause, behind the scenes, kind of nudging both of them along and explaining why they're linked.
So, imagine two friends who always wear similar outfits. It's not that they planned it. Something else is going on, right? Maybe they both love the same brands or have the same taste or shop at the same store.
You got it. That's a perfect example. And Reichenbach didn't stop there. He laid out four conditions a common cause has to meet.
Okay, now we're getting into the nitty-gritty. What are these four conditions and why do they matter so much for RCCP?
Well, the first one is that the common cause has to make those two events independent, meaning once you know the common cause is there, knowing one event doesn't tell you anything more about if the other one will happen.
Right, so back to the fashion friends. If we know they both shop at the same boutique, finding out one bought a certain shirt doesn't make it more or less likely the other one did too.
Exactly. The second condition is kind of the flip side. It says when the common cause doesn't happen, knowing one event shouldn't give you any clue about the other one.
So if they didn't shop at that boutique, knowing one friend bought the shirt has no impact on whether the other one did. It shows how crucial that common cause is for understanding why they're linked in the first place.
Right. The third and fourth conditions are more straightforward. They basically say the common cause has to make each event more likely to occur on its own.
So shopping at that specific boutique makes it more likely either friend will buy that shirt than if they hadn't gone there at all. These four conditions together, it's like a checklist for spotting real common causes, separating them from just coincidences.
Exactly. And for you as a philosopher, this has some really interesting implications. RCCP basically says when we see a strong connection in the world, we shouldn't just stop there. It's like a prompt to search deeper, to find the causal story behind it. It pushes us to uncover the hidden links that shape the patterns we see.
That's so cool. It means correlations aren't just like statistical quirks. They're clues pointing us towards this whole web of causes and effects tying things together. Does that mean RTCP has applications outside of philosophy too?
Oh, absolutely. People use it in epidemiology, economics, even linguistics when they're trying to figure out causal relationships from data.
Oh, right. I remember that example from the Stanford Encyclopedia of Philosophy about language descent, like the link between English words starting with F and Spanish words starting with P.
That's a classic. It shows how RCCP helps us understand historical connections. Those similar sounds point back to a common ancestor language, Proto-Indo-European, even though the sounds themselves aren't that similar anymore.
It's like a linguistic fossil, revealing a shared origin across languages that sound super different today. And what's amazing is the proof of this shared ancestry is in the correlation itself. The sounds don't even have to be phonetically similar. Like Latin do and Armenian urk, both coming from Proto-Indo-European roots, are obviously connected despite sounding completely different now.
That's the beauty of it. That example really shows how RCCP can uncover historical links and hidden causal pathways, even when the direct evidence is tricky or missing.
This is all mind-blowing stuff, but I'm pretty sure any good philosopher would know there's no such thing as a perfect principle. What are some problems people have brought up about RCCP?
Great question. One of the biggest challenges comes from quantum mechanics. Things get a bit weird there. You get stuff like entangled states, where things are connected without any clear common cause that fits Reichenbach's four conditions.
So, in the quantum world, things can be correlated without a common cause. That's crazy. It really makes you rethink the whole cause and effect idea we're used to.
It definitely does. And then there are these thought experiments like Cartwright's factory and random darts, where you've got these probabilistic correlations, but no obvious common cause that fits Reichenbach's rules.
These examples seem to challenge the very foundation of how we think about causes, probabilities, even what it means for events to be truly separate. Do these counterexamples mean RCCP is just plain wrong? Or are there ways to make sense of it all?
That's the million-dollar question. The debate is still going strong. Some people think these challenges show RCCT's limits, that maybe we need to tweak it, or that some parts of reality just don't fit the mold. Others think maybe we can resolve these issues with a deeper understanding of quantum mechanics or a more nuanced view of RCCP itself.
This is already a wild ride, and I totally get why RCCP is so captivating for both philosophers and scientists. One idea that tries to tie RCCP to the whole idea of time moving forward is the fourth asymmetry. What's that all about?
Yes, Reichenbach's attempt to explain why causes come before effects using these probabilistic forks. It's a clever idea, but it has some issues.
Well, we philosophers love a good puzzle. So how does this fork-case symmetry work, and where does it break down?
So Reichenbach focused on what he called conjunctive forks. These are situations where you have a common cause that happens before the effects it influences. He said these forks usually open to the future, meaning nothing that happens later can erase the correlation between those effects. Think of a group of actors. The lead man and woman get sick after a meal. The bad food is the common cause, and the fork is open to the future.
Classic food poisoning. So what's the problem with this asymmetry?
Well, a lot of times when we try to figure out what happened in the past, we're not looking at entropy, like how disordered things are, like Reichenbach thought. We figure out a city was bombed from the wreckage, not from seeing buildings still standing, even though the wreckage is more disordered.
Right, it's the evidence of the bombing that matters, not just how messy things are.
Exactly. Plus, in classical physics, every one of these conjunctive forks open to the future seems to be part of a closed fork, so the asymmetry kind of breaks down.
So the fork asymmetry is interesting. Trying to link RCCP with time's arrow and all, but it doesn't quite hit the mark. But this deep dive has already uncovered some really thought-provoking stuff. Where do we go from here?
Well, there's still a lot to uncover. Like, there's a modern idea that builds on RCCP, the causal Markov condition, which is a really powerful way of looking at cause and effect relationships.
A new and improved version, you say? That sounds like something we should definitely explore. But for now, we'll have to leave our philosopher friend hanging.
Don't worry, we'll pick up right where we left off in part 2 of this deep dive. Until then, happy pondering.
Welcome back. We're continuing our exploration of Reichenbach's common cause principle.
We've already dug pretty deep looking at what RCCP is and some of the challenges it faces, from those tricky thought experiments to the strangeness of quantum mechanics. Right. And remember, we hinted at something called the causal Markov condition, CMC, a kind of modern take on RCCP.
Oh yeah, the CMC. For our philosopher friend who might not be super into causal modeling, could you give us the lowdown on what it's all about?
Sure, the CMC usually hangs out with something called causal Bayes nets. These nets use diagrams called directed acyclic graphs, or DAGs for short, to represent how different variables cause each other.
Oh, you mean those diagrams with arrows connecting things, showing how they influence each other?
Exactly. Each arrow means one thing directly causes another, and no arrow means there's no direct link. These DAGs come with something called a probability distribution, basically how likely different values are for each variable.
It's like a map showing how causes and effects are connected, plus you've got probabilities for different outcomes, a way to visualize the whole cause and effect structure of a system.
Exactly. And the CMC itself ties these DAGs and probability distributions together. It says that if you know the values of a variable's direct causes, it's independent from everything else except its descendants.
So if you know what's causing a variable, it's basically cut off from all the other variables that aren't descendants. That sounds a lot like Reichenbach's screening off condition for common causes.
You're picking up on something important. The CMC actually leads to a generalized version of RCCP.
Really? So the CMC is like a bigger, more powerful framework that includes RCCP.
You could put it that way. It's easiest to see this through something called deseparation, basically how paths in a DAGN can be blocked or unblocked by looking at certain variables. Imagine two correlated variables in your DAGN that aren't directly connected. Deseparation says there has to be a path between them that's unblocked, and that unblocked path has to have a common cause.
So all the common causes would deseparate the correlated variables, meaning they screen them off from each other.
Precisely. That's the heart of RCCP. Correlations between things that aren't causally related should be explained by common causes.
Fascinating. The CMC not only covers RCCP, but also gives us a richer way to analyze cause and effect relationships. How does the CMC approach finding the direction of causality?
Well, RCCP used that fork asymmetry thing we talked about, but the CMC focuses more on colliders. These are variables where causal arrows converge.
So instead of forks opening to the future, we're looking for these converging arrows.
Exactly. Algorithms that try to figure out cause and effect relationships from data use these collider patterns as key indicators of causal direction. It's a powerful tool for untangling those relationships.
The CMC sounds like a robust tool for understanding causation, but I'm guessing it has its own set of assumptions and limits. What are some things to consider when using it?
Good point. One big assumption is causal sufficiency. It means we've included all the important variables in our model, so any other causal influences have to be independent of each other.
So we're assuming there are no hidden common causes lurking outside the variables we're looking at.
Exactly. Notice how this is kind of like a common cause principle itself. They both say that if variables aren't causally related, they shouldn't be probabilistically dependent either.
It seems like both the CNC and RCCP have this underlying philosophical thread. They both suggest correlations, especially between things that aren't causally related, should be explained by shared causes.
Precisely. But we have to remember we're working with models and assumptions. There's always a chance there are hidden variables or complexities our models miss.
Right, there's always the possibility of the unknown messing with our understanding. Which brings us back to those challenges to RCCP, especially those from the bizarre world of quantum mechanics.
Yes, the quantum realm, where our normal ideas about cause and effect often fall apart.
I'm really curious about what RCCP means for those mind-blowing EPR correlations.
Perfect timing. EPR correlations are the perfect test case for RCCP. They make us wrestle with big questions about locality, causality, and the very nature of reality itself.
And we're back for the final part of our deep dive into Reichenbach's common cause principle, exploring its philosophical side.
Where we've been examining its strengths and weaknesses, and now how well it applies to the most mind-boggling area of all, quantum mechanics.
Yeah, we left off on a bit of a cliffhanger, ready to tackle EPR correlations, one of the biggest challenges to RCCP. For our philosopher friend out there, could you give us a quick explanation of what makes these correlations so strange?
Sure. Basically, EPR correlations involve these pairs of particles linked in a way that even when they're super far apart, they still show correlations in their properties that just don't make sense with classical explanations.
So, like, imagine two coins flipped at the same time, always landing on opposite sides. Even if one coin is here on Earth and the other's on the moon, it's like impossible unless there's some faster-than-light communication going on.
Exactly. And that's exactly the problem that Einstein, Podolsky, and Rosen, the EPR and EPR correlations, pointed out. These correlations seem to break the rule of locality, the idea that physical influences can't travel faster than light.
So where does RCCP fit into this whole quantum mess? Can it explain these spooky correlations without resorting to faster-than-light communication?
That's where things get super interesting and kind of tricky. RCCP, at least how it's usually understood, says the common cause has to happen before the correlated events.
But if the events are space-like separated, meaning no signal could travel between them without going faster than light, how could there be a common cause in their past?
That's the challenge EPR correlations throw at RCCP. They make us wonder if there might be other ways to explain these correlations besides a common cause in the particles' shared past.
So does that mean RCCP just fails in the quantum world? Is it the end of the road for the common cause principle?
Not necessarily. There's been a lot of discussion and research looking into whether hidden common causes could still explain EPR correlations, even if they're not in the particle's past.
Hidden common causes, you mean factors we haven't thought about or can't even directly observe?
Exactly. Some people have suggested that maybe these hidden common causes are working at deeper levels of reality, or perhaps the correlations are set up beforehand in a way we don't understand yet.
It's like those mystery novels where crazy stuff happens and then it turns out there was this hidden connection or secret plot all along.
A perfect analogy. But this search for hidden common causes leads to important questions about locality and the idea of no conspiracy.
Now we're getting deep into philosophy. What do locality and no conspiracy mean here?
Locality, as we've talked about, means that physical stuff can't influence things faster than light. No conspiracy means the universe isn't like trying to trick us.
So there's no puppet master out there making these correlations that seem to break the rules of physics.
Right, and when you add both locality and no conspiracy to possible explanations for EPR correlations using common causes, the options become even more limited.
Limited how?
Well, there are different types of locality: surface locality, which we can test, and hidden locality, which deals with those unseen common causes and can't be directly tested. And no conspiracy has weak and strong versions, each with different restrictions on how common causes can influence events.
So what's the bottom line? Can we say for sure whether hidden common causes can explain EPR correlations while still sticking to locality and no conspiracy?
That's a great question, and it's still an open question. Some research suggests that certain hidden common cause explanations, specifically those with strong no conspiracy and hidden locality, are ruled out by these no-go theorems.
So some options are out, but not all of them.
Exactly. The possibility of weakly, non-conspiratorial common causes that respect surface locality is still a possibility. It's an area that needs more investigation from both scientists and philosophers.
This deep dive into RCCP and EPR correlations has been seriously thought-provoking. It feels like we've barely scratched the surface of these big questions about causation, correlation, and what reality really is.
It shows how powerful Reichenbach's common cause principle is. It's still sparking these deep questions, even when faced with challenges from quantum mechanics.
So for our philosopher friend listening, what are the key takeaways from our RCCP exploration? What should they be thinking about as they continue their intellectual journey?
First, I'd say, remember how important RCCP is for understanding causation? It pushes us to dig deeper, to find the causal explanations behind the connections we see.
Yeah, it's a call to look beyond the surface, to figure out the hidden links that might be driving the patterns we observe.
Second, remember that quantum mechanics, especially those EPR correlations, show us that our usual ideas about cause and effect might be limited. They suggest there might be more to the story than we currently understand.
Hidden variables, deeper levels of reality, pre-established harmonies, it's all worth exploring.
And finally, I'd encourage our philosopher friend to embrace the ongoing conversation between science and philosophy. These questions about causation, locality, and the very nature of reality need both rigorous scientific investigation and deep philosophical thought.
It's a good reminder that to really understand things, we need both science and philosophy, weaving them together to get a more complete picture of knowledge. So to our listener, keep asking questions, keep exploring, and keep diving deep into the mysteries of the universe. Until next time.